Hi there, this is a review of displaying data for AP Statistics. This is lesson 3. So remember, in lesson 2, which I suggest you watch if you haven't, we learned how to describe data by SOCs. Remember that acronym? Now let's look at how the data is displayed in the first place. Well, there's lots of different things that we can do. One is a dot plot. Dot plot, maybe you've seen this before, but it's pretty straightforward, honestly. Each data point is displayed as a dot, and you draw the dot wherever the data is. So that's pretty easy. And obviously, you can tell like a mode by that easily. And you could assume that 13 is an outlier. Then there's also stem plot. Sorry, I dropped something. Stem plot. This is something, if you see that all the different data here, it tells you 1, 1 equals 1.1. So that means the data is 1.1, 1.2, 1.4, 1.6, 1.6, 1.7, 1.9, 1.9, and you can see how it's going there. What skew is there? You might think, how could you tell a skew? Well, if you think about it, really, this is kind of like this is sort of like you could turn this over, so there's a right skew. If you see that we turn this sideways, it's almost like now it's starting to look somewhat more like the dot plot that we just saw. Remember what I always say, to tell what skew there is, imagine if you're at the top of the hill, what way do you go? You would go to the right. If you're on a skateboard or something. So that's how you know it's a skew to the right. You would just want to turn that sideways. Histograms, that's pretty frequently used. So what are these? Well, they're basically just number bar graphs. When we think of bar graphs, usually the places where you put stuff, the x-axis might just be quantitative data. Like when you're in elementary school, maybe you had something like colors or something. But we have numbers when we're using histograms. And we use frequency histograms. What is a frequency histogram? That means that the x-axis shows a frequency or a count. So see how it's 1, 2, 3 here? That's saying how frequent is that data? So here's something important, bin width. What is a bin? A bin is just a section. See this section here? That 0 to 5, 6 to 10, that's a bin. Now, a bin, it's important to look at the width. So if the x-axis sections are a smaller range, so in other words, if the bins don't show that much, they're only a small section, like right here, 0 to 3, 3 to 6, that's not that much. Then there might be only one rectangle per section, because think about it, if and on the other hand, if they were large, then there will be more. So here's what I mean by this. See this data? 1, 2, 7, 10, 17. Here we have small bin widths. So it's like, there's only one square. That's the highest thing that there is. And it's a little bit better once we go up to 5, because if you see now we have 2 for some of them. So it's important to look at bin width. Well, how would we choose what a bin width is? Now, I'm just telling you this. I'm going to show you how to do this put this into the calculator, so you don't even have to worry about that. But I'm just going to tell you how you would do that. So you put the numbers in order. So see these numbers? All right, let's put them in order. There you go. Now, to show what the intervals will be, so remember how before we had 0 to 5, how do we figure that out? Well, we're going to do the highest number divided by the number of bins that we want. It kind of just depends, but let's just say we wanted 5. So the highest number is 34. So that means every interval should be 7. And I just realized something. I accidentally did this backwards. So pretend like we want 7 bins, then it would be about 5. So each interval is going to be 5, 0 to 5, just like before. So then we make it. So we see there's 7 different bins. 1, 2, 3, 4, 5, 6, 7. Because like I said, I did this backwards. So pretend that that's 34. Here, let me just draw it. So no, don't want that. Pretend that it's instead we want 7 bins, so that's approximately 5. So if you see when that's how it works. So there you go. But we can also put it into the calculator. So here's the steps of what you do. Now, I'm going to try to see if I can show you this. Okay, so I think this is the only way that I could do this. So sorry about that. Let's go back on that. So how do we put this into the calculator? All right. So we're gonna push. By the way, if you want this thing that I'm using, go to Wabbit.emu. But it's definitely better to have your own calculator. But anyways, let's push stat. So edit, and we're going to add the data. Remember, I already showed you how to do this in the last thing. So I'm just going to make up some data. All right, that's fine. All right. So now we're going to push second Y. All right, we're going to choose plot 1, so enter. We're going to turn that thing on. We're going to choose the histogram 1. So it's not on histogram right now, it's on the line, because that's probably the thing that you usually use in algebra. So we're going to do that. Now we're going to push zoom, and we're going to push 9, because if you see the thing that is number 9 is zoom stat. So we could just push 9. Ooh, well, and there you go. Now we have our histogram. So how would you determine the bin widths? Well, the highest number I put in there was 45, and we see the different bins. There looks to be 5. So we could say that each interval is 9, so 0 to 9, and so on. So let's make this thing full screen now. All right. Relative frequency histogram. Well, this is just if you show proportions, but usually percentages on the y-axis. But we're not going to talk about that much right now. But that's an example. Because remember, this would be 40% up here, like that. Okay. Box plot. This is something that might seem a little bit crazier. Maybe it was easy to tell what the other ones were, but this one seems a little bit crazy. You might have learned about it, you might not have. But really what these show is simply just the 5-number summary. Because remember, lowest, quartile 1, quartile 2, or median, quartile 3, highest. So the line that's in the middle of the box is the median. Each edge of the box is quartile 1 and 2, and then the lines extending that shows the lowest and highest values. Usually there's like a thing like that on the end, but that wasn't the case for this. Sometimes there's dots or squares that are not on the line, and that means it's an outlier. Height doesn't matter, so it doesn't matter how high or low we go. It doesn't. We can make it high, we could make it hardly high. But these, like anything else, these can be skewed too. How do you know what skew there is? Well, it's the line in it. If it looks like like the line separating it, if you see 2 squares, if it looks like the squares are equal, then there's no skew. If it looks like the square to the right is bigger, or rectangle, I should say, then that's right skewed. And if the one to the left is bigger, then that's left skewed. Or basically, as usual, it seems backwards. The line goes to the right, it's left skewed. The line is to the left, that's right skewed. But skew doesn't, it doesn't, skew is not based on how long these lines are that extend out from the box, which are called the whiskers. The whiskers don't say if it's skewed, the line does. All right, box plots in the calculator. Oh, we can do those too. Luckily, we don't have to do that. So we had a bar or histogram. So why don't we instead make it a box plot? So we already typed our data in, so we don't have to do that. So let's skip over to step 3. All right, this time we're going to do enter again. This time we're not going to do this one. We're going to do this one. Oops. Guess I'll just have to go to the right. If you see there's 2 box and whisker plots, we're not going to use that one because if you see that there's 2 dots beside this, that's the outliers, and we do want outliers. So never do that one, only do that one that it's on right now. So enter, and we can even choose what mark the outliers are. Do we want the outlier to be that, square, or a dot? I'll just do this, or a plus or a dot, I meant. All right, so now we're going to push zoom 9, and it shows that stupid thing. And if you see, this is slightly bigger, the rectangle to the right is slightly bigger. That means that it is skewed to the right slightly, but not that much. All right, there you go. At least we don't have to do those things ourselves. Oh. Okay. Usually I just stay in the slideshow. Am I still recording? Oh. Yeah, I think I am still recording. Okay, sorry about that. I don't know what happened. All right, AP practice. We all know that when you learn things in an AP class, it's all fun and games until you have to do a stupid question. You got to be careful. Sometimes you can know the content completely well in a class, but then guess what? You don't do well in the exam because you realized that you didn't know how to answer the questions. We all know the real goal of taking an AP class is to get the credit. If you didn't get the credit, then there's no point. It doesn't matter if you have super high grade in the class because you didn't get the credit. You might as well, I mean, sometimes it can help your GPA, at least that, but there's 2 things to an AP class. The first thing is to hack knowing the content. Hopefully by this video, we can do that. But the second thing that's equally important, if not more important, is to know how to answer the questions. Because if it's either one. If you don't know one of the things, you can't pass. If you don't know the content, but you know how to answer the questions, that's usually not the case, but you wouldn't pass because you couldn't even answer the questions right. You might know what it's asking, but you can't answer it because you don't know anything. But if you know the content, but you don't know how to answer the question, like if you see this and you're like, oh, so many words, I don't even know what it's asking, but I know the content. Well, that's not going to help you either. So let's figure out what kind of questions. This is a free response question. Let's see. They always have to do dumb things like this, where it's long, but that's just how they are. So it's always good to underline things. So I'm going to just do that for us right here, all right? There you go. That makes it seem a lot easier because there's a lot of stuff that doesn't matter. So let's just read the underlined things. So, well, we can, I guess I'll just read the whole thing. Okay, to determine the total or the amount of sugar in a typical serving of a breakfast cereal. Okay, student randomly selected 60 boxes of different types of cereal from the shelf at a large grocery store. It doesn't matter that it's a large grocery store now, it doesn't. A student noticed that the side panels of some of the boxes showed sugar content based on 1 cup servings, while others showed 3/4 cup servings. Numbers are key, so that was probably the most important thing. Many of the boxes that showed 3/4 cup servings were the ones that appealed to young children. So we know that the cup servings appeal to young children more than the 1 cup ones. So they wondered if there might be a difference in the sugar content of the cereals. To investigate it, they separated into 2 groups. One group has 29 cereal boxes with the 1 cup servings, and the other group has 31 that have 3/4 cup servings. So 29 plus 31, that's the 60 boxes that they had. That really doesn't matter, those numbers. We just need to see the difference. So they made box plots showing the sugar content in grams. And remember what the box plots tell us? They tell us the quartiles, they tell us the minimum and maximum. All right, so we see that there, we're looking at it, okay. And we're gonna probably have to make some comparisons. Oh yeah, what do you know? That's what it says. Write a few sentences to compare the distributions. Well, how do we do that? Well, we know socks, but we're gonna get to that. We're gonna look at the other things. I mean, technically, maybe we would just want to answer A first. So I guess we'll just do that, all right? Let's go to A. So let's compare the graphs here. We're going to use socks. So here's an example response of what someone could say. We can notice that they have a serving size, the one that has a serving size of 1 cup, see this top box plot, it has a median sugar amount that is larger than this one. How do we know? Well, this line here, see, it's more this way. See, 12 for this one, 10 for this one, so it's bigger. So we can just say that. That's our C in socks. There is more variability for the 1 cup cereals. More variability. How do we know? Well, look, it covers a more extensive area, more range. See that? And that is our S spread in socks. All right, then another thing, the shapes of the 2 distributions differ. So now we're on S. O, we're not going to say because we don't see any outliers, do we? The distribution of the sugar content for the 3/4 cups one is symmetric mostly. Oh, how do we know? The 2 rectangles that there are about the same size. But this one is skewed left. How do we know? Because this is a bigger one on the left, bigger. So let's say this is your reader. What would he say? Reader Corral? They know their socks. So they would be glad about that. All right. All right. Well, we're not done, are we? Because they have another stupid thing. They always have things like this. Oh, the students realized that something was dumb, so they changed something. I mean, if you took AP Physics, that's what it's like in that too. After analyzing the box plots on the preceding page, they decided, oh, instead of a comparison of sugar content per recommended serving, so instead of 1 cup and 3/4 cup, they're going to make it equal size servings. So they decided they're going to make it both 1 cup. Well, how can they do that? They decided to multiply the 3/4 cup by 4/3. That makes it equal 1. So now that's the reason why they look different. See, the 1 cup is the same, but the 3/4 cup is different because they multiplied it by 4/3. Why? They did it so that they would both be based on the same thing. That's why this one was inaccurate that we just looked at. All right. The box plot is shown below now. So the new thing. What new information does it provide? All right, let's see. Well, what is this saying? Well, it's basically saying how is it different before and after? What's the difference? Well, what you could say is there's no change in the distribution for the first box plot because nothing was changed to that. They didn't multiply anything for the 1 cup because they were trying to make them both based off of the 1 cup. So obviously we could say that, but for the second box plot, there is definitely a shift. Yeah, of course. If you multiply something by 4/3, of course there would be a shift. So if you see it shifts over to the right and it shifts towards higher sugar content. So it wouldn't be good to say it shifts to the right. Let's say it shifts to higher sugar content because that's what it does. Also, see, also, you have to say as much as you can. Both box plots now share a similar maximum value. Look, the maximum value, that's the end of this whisker. It's not similar there, but it is here. What would they say? They can compare. So that we're on a roll, but we're not done with this stupid question. We have one more thing. Based on the box plots shown, how would you expect the mean amount of sugar per cup to compare for the different serving sizes? Ooh, that one seems a little bit strange. And they say explain, so that's how you know they definitely want something. Mean amounts. Oh, does that mean it's something that's rude? No. Hopefully remember what mean is, the average. So how does the average amount of sugar cup compare for the different ones? How does the averages compare? Well, how can we compare averages? We can look at how symmetric they are. And here's something, if I didn't already say it or if you didn't know, symmetric, if something is symmetric, remember that for a box plot, that means that each thing is equal. See, like right there, each square divided by the median is equal, or a rectangle. See, they're pretty similar shapes. They're not there, but if they are, then that means the median equals the mean almost, not exactly, but it pretty much, they're the same, if that's the case. But if it's skewed left, that means the median is greater than the mean. Well, that makes sense because see, the median is like, it's like all the way over there now to the right. And this is skewed to the left because this thing's bigger. That's to the left. If it's skewed to the right, which is not the case for this, if it was the other way around, like that line was there, then the median would be smaller than the mean, because think about it, the median's more to the left, the mean's not in that case. So here's what we could say. For the 1 cup serving, so this top one, the data is skewed left. All right, we already know that. Because it didn't change, this is the new graph, it didn't change. For the 3 quarter cup serving cereals, oh, so now we're down here. It's fairly symmetric. Oh, wait, sorry, I skipped something. Since it's skewed left, the median is likely greater than the mean. Well, look, the median's all the way over there, so it's likely greater than the mean if it's skewed left. That's something you need to remember. But for this one, it's fairly symmetric, so we could say that the median and mean are similar. In conclusion, so if the median is greater than the mean, then that means that the mean is likely smaller for this one. So we can say that the mean sugar in the 1 cup is smaller. So the mean cup of sugar per cereals with 1 cup serving is less than the mean for the cereals with a 3 cup serving size. So the mean, how do we know? Well, like I said, the mean and median are pretty equal here. So that means the mean for this one is about 13. But for this one, since it's skewed left, the mean has to be less than this since it's skewed left. So the mean's somewhere over here. So that's how we know it's less. They know about skew. So thanks. Thanks for watching this. I hope that helped. Those can be kind of tricky, but that's what you got to do.